In this section, we're going to be talking about angles. That is to say, we're going to talk about the definitions and the vocabulary that will be necessary going forward for this course. All right, so when we talk about an angle, we're talking about a pair of rays. So if you take one ray, starting from a point, we'll call it the point A, out to some other point, B, but then continuing on past B, here we have one ray. Now, if you draw a second ray, starting from the same initial point A, but going through some other point, which we can call C, and continuing on that way, here we form an angle. Here, this angle has a common point between the two rays. This is called the vertex of the angle. Now, when we label an angle, there's a couple of ways of labeling it. One way is to use the 3 points that we use to create these two rays. The vertex is always named in the middle. So you could say the angle from BAC, or you could equivalently say the angle CAB. It doesn't matter what order these are in as long as the vertex is in the middle. To make extra clear that we're talking about an angle and not these separate 3 points, we put this little symbol in front. This little symbol that looks like a little angle. Right? So this would be read as the angle BAC. This would be read as the angle CAB, and both would refer to this. However, we can also refer to it a little bit differently. Here, this angle, you could think about it as something made up using these 3 points, or you can think of it as something made using these 2 rays, or you can think of it as an object in and of itself. This is one thing, one angle. When you think about it that way, it often doesn't make sense to label it with something like this, so we have a different convention. We label the angle with just a single letter, and that letter, to distinguish it from points or lines or other notation that we use in algebra, here we're going to use a letter from the Greek alphabet. Any letter would actually work. You can use a letter from the standard alphabet, or you can use an uppercase or a lowercase. But the convention is we want to go ahead and use a Greek character. The most common of these is this symbol, which is read as theta. However, there are others that are commonly used. For example, alpha. There's beta. There's gamma. And there is phi. These are just a convention. These are commonly used letters for the name of an angle. However, you can use any letter you like. Theta, however, is by far the most common. And if you only ever have one angle, it's probably called theta. Now, once you have an angle, the next question is, how do I measure that angle? Well, before we measure, we have to figure out which direction we're measuring in, because it makes a difference if we measure from this ray to this ray, how far that is, or if we measure from this ray to this ray, because that's much further if we go this way, or it's the opposite direction if we go this way. So because we can reach from here to here or from here to here a few different ways, we have to be a little clearer. Whenever you measure an angle, one of those angles is the one you're going to start measuring from. The other one is the one you're going to end at. The one you start measuring from, this is called your initial ray. The one that you end on, now remember they do have to have a common vertex. The one that you end on, this is called the terminal ray. Switching these two would give you the same measure, but in the opposite direction. And there will be a difference between going from here up this way versus from here down this way. Those are considered to be different measures. Okay, but once we decide for a particular angle, okay, I'm going to measure from here to here, how do we measure? Well, there's a couple of ways. The first one that we're going to see is what's called the degree measure. If you were to take a circle and cut it up into a lot of little slices, oh, how many slices? Well, it's too many for me to draw here. Here I've cut it into 4 slices, I've cut it into 8 slices, I can cut it into 16 or 32, but that's still way too big. What we want to do is we want to cut it into 360 equal slices, which of course I'm not going to be able to draw here. But if you were to do that, if you were to cut it into 360 individual slices that are all the same width, the same measure, then each one of those would have a measure of 1 degree. So 1 degree, that's written as, instead of writing the word degree every time, we use the degree symbol, which is a little circle up here. It's not the number 0, it's actually just a little circle, and this is read as 1 degree. If you look at a circle, a full revolution all the way around the circle has 360 degrees. So here, one circle has 360 degrees. Okay. So now with that, let's get back to measuring. When you measure an angle, you care about where you started and where you're going to end up. So the direction is going to matter. Here I'm going counterclockwise. That would be different as if I were going clockwise. However, one thing that doesn't matter is the position of these rays. For example, if I have those rays and I measure and I get an answer, if I go from here to here, if I then slant that over this way, these have moved, but that's still the same angle. I haven't changed anything. If I were to rotate it the other way, these would still be the same angle. Nothing's actually changed. So, aside from caring about a measure from one ray to the other, or vice versa, we also have to worry about, well, what happens if we end up rotating things? Well, what we end up doing is saying, you know what, let's not worry about it. Whenever we consider an angle, what we're going to do is we're going to measure it in standard position. All right, so what does that mean? An angle is said to be in standard position and of course not every angle that we see has to be this way, but this is if we have our choice, if it's up to us, we will almost always work with things in standard position. An angle is said to be in standard position if its vertex, that point right there in the corner, if its vertex is at the origin of the XY plane, and the initial ray, the one you're starting from, is on the positive half of the x-axis. So if we have an angle that's here, or here, or here, where it's changing its position, its orientation, or whatever, all of those would be considered the same measure. So instead of having to measure it wherever it lies, what we do is we say, okay, what angle do you want to measure? That one there. Okay, pick it up, bring it over here, and put it somewhere that's nice to work with. On our XY plane, our angle will have its initial ray on the positive half of the x-axis with the vertex on the origin. So you would start from the origin and this way, positive half of the x-axis. This is your initial ray in standard position. And then your terminal ray would be wherever it lies. For example, something like this. And the measure of your angle, which we're going to call theta for now, would be measured from the initial ray, always starting from the positive half of the x-axis to the other angle, to the other ray right here, the terminal ray. Now, once you have an angle in standard position, measuring is a little more simplified, because now we don't have to worry about where the initial ray is. We always know where it is. We just have to know where our terminal ray is and the measure to get there. Now, mind you, if you start from this ray and go to this ray, there's two ways to do that. This way that I've drawn in red, or you could go back this way. Both of these are perfectly valid measures. You could measure this or you could measure that. But we don't want any ambiguity. When we measure an angle, we want to be absolutely certain of what we're measuring. There's nothing wrong with these two, but we don't want to have two answers. We want to have a unique answer. We want to be able to be sure of what we're talking about. So whenever we measure an angle, we're going to measure it from wherever it is. We're going to go ahead and put it in standard position. And the measure that we want is this one. That is to say, the one that's going counterclockwise. So here, a positive measure of an angle is in uh, in a counterclockwise orientation. And you say, well, does that mean I can never do it this way? You can. That would just be a negative measure. So for example, an angle like this would be 10 degrees, 20 degrees, 40 degrees, 72 degrees. An angle like this would be negative 100 degrees, negative 120, negative 175. It would be a negative measure. So here, a negative measure of an angle is in the clockwise orientation. Okay, now we have seen that a circle, a full revolution, is 360 degrees. Well, right here, if I'm looking on the XY plane, each quadrant would hold 1/4 of a circle that was centered at the origin. So if I had a circle like this, the 360 degrees that make up its full rotation would be equally divided into these 4 quadrants. Oh, okay, well, 360 divided by 4 would be 90. So right here, if this is my initial ray, which in standard position it always will be, then if I start here and I don't open the angle at all, well, then the measure is 0. However, if we open the angle so that it rotates around this way and does a quarter rotation, a full rotation would be 360 degrees, a quarter of that would be 90. So right here, if you have an angle that faces straight up, where the terminal ray faces straight up, that would be 90. Now remember, we're talking degrees. The number 90 doesn't mean anything unless you have a unit here, so that's 90 degrees. Now you might wonder, well, why do I need the degree symbol? If I'm talking about an angle, then 90 must mean 90 degrees, right? Well, no, there's other ways of measuring angles, which we'll see in a few minutes. So this will distinguish degrees from what we'll be calling radians in a few moments. But if you keep going around, another quarter circle, that's another 90. So 90 plus 90, that's 180. Another 90, that's going to get me to 270. And another 90 would get me back to 360. So you would start at 0, 360. You would start at 0, and if your terminal ray was also here, that would be an angle of 0. If your terminal ray was here, that would be 90 degrees right there. If your terminal ray was here, that would be 180. If the terminal ray was here, it's 90 degrees this way, but remember, we were measuring counterclockwise. So that would be 270, and if you go all the way around, that's 360. But remember, these quadrants contain everything in between those angles separated by 90 degrees. What that means is, depending on where the terminal ray of your angle lies, you get a range for what your angle could be. Meaning, if you have an angle that's between 0 degrees and 90 degrees, you know that the terminal ray is going to be in the first quadrant. You know that one of your rays will be on the x-axis, and your other ray will be somewhere in here. Or the other way around is also true. If you see an angle that's in standard position, and the terminal ray ends here in the first quadrant, you know its measures between 0 and 90. So the way an angle looks can give you a range as to what its measure might be, and what its measure is can give you a decent range of what it might look like. All right, so for example here, if an angle in standard position has a terminal ray in quadrant number 3, then we know that its measure must be between, well, our 180 and our 270. Then its measure is between 180 degrees and 270 degrees. Now notice that that does mean that we have a couple of angles that don't fall into any of these quadrants, because the quadrant is everything in between 0 and 90 degrees, everything between the positive half of the x-axis and the positive half of the y-axis. Same thing for anything. The second quadrant would be between these two rays, third quadrant between these two, and fourth quadrant between these two, which means that the rays that are actually on the axes, on the 0 degree, 90 degree, 180, or 270 degree, those wouldn't lay in any quadrant. Those are separate, and those are called the quadrantal angles. I'm a little tongue-tied right now. So here, a quadrantal angle has its terminal ray on an axis. So for example, 0, 90, 180, 270. Like this. Now you might say, well, what do you mean, for example? I mean, that's it. That's all 4 of them. You don't really need to say, for example, if you've just told me every possible outcome. Well, that's not every possible outcome. Because you say, oh, well, I guess 360. Yeah, okay, so you have one more? No, we have a lot more. Because whenever we measure an angle, right here, we've gone all the way around a circle and gotten 360 degrees. At first, that makes it seem like 360 degrees is the biggest angle. But you can keep going. Because here, if you have an angle that has a common point here, that's our vertex. You have 0 degrees, you have 90 degrees, you have 180 degrees, 270, and if you roll all the way back around, this 360. But you can keep going. That'd be 361, 362, 363, 364, 365, and so forth. So your angles can actually go beyond 360. It just means you're doing more than one rotation of your circle. Okay, but then let's go back a bit. I said, don't forget to put this little symbol here because it tells us that we're dealing with degrees. And there's going to be another way of measuring an angle. Okay, well, what's that other way? Okay, so our next part, let's go ahead and talk about the alternative way of considering the measure of an angle. A circle is a good way to think about measures of an angle because a full rotation of a circle is going to give us 360 degrees, and any angle we could think of is going to fall somewhere on this circle. Even if you go past 360 degrees, your terminal ray will still fall somewhere on this circle, yeah? Even if you go, that's 360 degrees, and then you do another 30 degrees, okay, well, your terminal ray still comes in contact with the circle. The circle comes in contact with any possible terminal ray, no matter what angle you happen to have. Okay, so then a circle is a decent way to help us think about angles. In particular, the outer edge of a circle. The outer edge of a circle will come in contact with any angle we can think of, as long as that circle happens to be centered at the origin. Oh, well, the outside of a circle is called its circumference. And we can measure the circumference of a circle. We have a formula for that. Recall, this is something from geometry. The circumference of a circle is circumference equals 2 pi r. To keep things very simple for us, we're going to go ahead and think of this circle as having a radius of 1. This is called the unit circle. The unit circle is literally just a circle whose radius is 1 unit long. This is the unit circle. Okay, so the circumference of the unit circle For this unit circle, c is equal to just 2 times pi. Okay, so one way to think about the measure of an angle is to think about, okay, well, what's one full rotation of a circle? Cut that into equal parts, make them all very small so that we have a good refined way of measuring even small angles, and we choose the number 360. And so each one of those is 1 degree all the way around a circle. But if we think about it this way, we say, well, going all the way around a circle is also its circumference, and that circumference is 2 pi. So we can say all the way around the circle is 360 degrees, or we can say it's 2 pi. 2 pi what, though? Well, we have a definition here. Let's define what a radian is. Definition. Let theta be an angle in standard position We know what standard position means. It means that the initial ray is on the positive half of the x-axis. Its terminal ray is somewhere else, which we will draw here in just a moment. Now, if that angle that we're going to draw here, we've already drawn one ray, we need the other one here. If theta intersects the arc of a circle centered at the origin, like this one is here, we have a circle whose center is at the origin, centered, oops, I don't know how to spell, centered at the origin, that is equal in length to the radius of that circle, then we say theta is exactly 1 radian in measure. So that's what we mean by a radian. Okay, this is one of those definitions that's better seen drawn out. We have a circle who's centered at the origin. Now, for simplicity, for the simplicity of computation, I've made this the unit circle with radius 1. This actually does work for any circle. Okay? But here I'm going to do it on the unit circle to make our computation just slightly easier. If we have an angle in standard position, with the initial ray on the positive half of the x-axis, that crosses a circle so that the arc that it crosses, that's this arc right here, it has some length. I can measure how long that is. I'll call that length S. Okay? If that S is equal to the length of the radius of this circle, then this angle in here is called 1 radian. Of course, if S is any bigger than the radius of the circle, then that means that you have more than 1 radian, and if it's any less, then you have less than 1 radian. But 1 radian means that the arc length here is exactly the same as the radius of the circle. If this is a unit circle, the radius is 1, that means this arc length is 1. If radius is 5, well then this arc length is 5. These two would be equal. Okay, but what if it's not 1 radian? What if these are not equal? Well, again, if S is bigger, then you have more than 1 radian. But we can be a little more precise than that. The measure of theta is going to end up being S over R. Okay, the measure of any theta, whether it's 1 radian or not, is S, which is the length of the arc, over R. Okay? Or you can also think of it, which also means you can say, well, theta is equal to S over R. You can multiply R on both sides, and you could say that also means that the arc length is equal to R times our theta. But on the unit circle, r is equal to 1. So here note, since on the unit circle, r is equal to 1, then on that same unit circle, you would have the arc length is equal to your angle. So on the unit circle, we saw that the circumference of the circle all the way around would be 2 pi units, 2 pi inches, 2 pi feet, 2 pi miles. Well then on the unit circle, whatever the arc length is, that's the exact same thing as the angle measure. So if we go all the way around the outside of a circle, that circumference is 2 pi, which means if we go all the way around a circle here, that measure will also be 2 pi. So the total measure of one rotation of our circle is 2 pi. This right here is actually a unitless measure. What do you mean by a unitless measure? I mean, it's not feet, it's not inches, it's not miles, it's just 2 pi. It sounds a little weird, but there's no unit to this. Because if you think about it here, theta equals s over r. If s is in inches, then so is r. Right? If this is 10 inches, then this is 10 inches. Or if this is 12 inches, this is 5 inches. So when you divide those, the dimensions basically drop out, and you're just left with a number. So here, this is a unitless measure. So if ever you write a number in reference to an angle, you always mean radians. And that's why we need the degree symbol here. Because if we write just 90 without the degree symbol, we mean 90 radians. Degrees are not unitless. They have the unit of a degree. Radians are unitless. That being said, some people feel a little uncomfortable using a unitless measure. So even though this doesn't have a unit, some people will still basically write it as if it does. So after the measure of the angle, if you're working in radians, you don't actually have to put anything. Feet, miles, you definitely don't put degrees. But some people like to put RAD for radians. This is optional, but it sometimes clarifies things, especially if you happen to be dealing with numbers like 5. 5 radians, or did you forget the degree symbol? Oh, let me clarify by writing radians. So sometimes it's helpful to write it, but it's not strictly necessary. Now, we have 2 ways of measuring around a circle. The number of degrees around a circle is 360. The number of radians around a circle is 2 pi, which means those two are equal to each other. Since 180 degrees, 360. Since 360 degrees, the full rotation of one circle, is equal to 2 pi, and I'm going to write the word radians, I'm going to write rads here. Not strictly necessary, but I do want to make sure that we see that we're comparing the two. 360 degrees is equal to 2 pi radians. So to convert back and forth between the two, you can just divide. If I divide here on both sides, if I take my 360 degrees equals 2 pi radians, I can divide both sides by 360. This gives me 360 degrees divided by 360, that's just 1 degree. 2 pi over 360, well, let me leave the pi alone. 2 over 360 reduces to 1 over 180. So this would be 1 pi over 180. So 1 degree is equal to pi over 80 radians. If you take that same equality, 360 degrees is equal to 2 pi radians, and instead of dividing both sides by 360, we divide both sides by 2 pi, then we get a conversion the other way. That is to say that, well, let's see, 360 divided by 2, that's 180. Now your pi stays on the bottom, so 180 over pi is equal to, this is 1 radian. So 1 radian is equal to 180 over pi degrees, and 1 degree is equal to pi over 180 radians. Which means that in spite of having 2 measurement systems, 2 ways of measuring, we can convert back and forth between them very easily. So for example here, let's convert from degrees to radians. If we have 45 degrees, to convert from degrees into radians, just note that 1 degree is equal to pi over 180 radians. So here what we can do is we can say, well, if 1 degree is equal to this, then 45 degrees, I'm basically just multiplying both sides by 45. So here 45 degrees, I can go ahead and multiply by pi over 180, and then that reduces. 45 over 180, that's going to give me 1 over 4. And then the pi stays right where it is. So I end up with pi on top. 45 over 180, that's 1 over 4. And that gives me pi over 4 radians. Well, that's a degree sign there. Yeah, like that. So 1 degree is equal to pi over 180 radians. So then 45 degrees is just that amount times 45, which gives me pi over 4. You can go the other way around as well. Convert from radians to degrees. And that's going to be, let's do pi over 3 radians. Okay, well, 1 radian is equal to 180 degrees over pi. So if I'm going to convert this number of radians, well, if I multiply this by pi thirds, I get what I want, which means I have to multiply this by pi thirds also. Okay, so multiply that by pi thirds. Here I end up with the pi's cancel out, and I get 180 over 3. That gives me 60. So to go from degrees into radians, I multiply by pi over 180. To go from radians to degrees, I multiply by 180 degrees over pi. Exactly why we want 2 different systems for measuring degrees versus radians will become more apparent later. Basically, degrees are easier for most people to imagine. It's easier to visualize for most people. And radians tend to work nicely in formulas. But they each have a purpose, which we'll see later. Now, we can, of course, run into an angle of any measure. We can run into angles that measure 7 radians. We can find angles that measure 15 degrees. Any possible angle could arise in any situation. However, there are some angles that are way more common. There are some that happen in application and problems, and they just naturally arise. So let's go ahead and show some of the more common angles that we'll be using in trigonometry and in the use of trigonometry. As mentioned earlier, a circle is a decent way of visualizing angles. So a lot of the times when we draw angles and things about angles, we'll be drawing them in relation to a circle. To simplify our computations, we almost always want our circle with radius 1. It's called the unit circle. So this is the unit circle. This is got a radius of 1. And it's used as a visualizing aid to help us see things. All right, so there are some angles that are way more common and useful than other angles. We're going to write them here both in degrees and in radians. It's useful to memorize at least one set, either the degrees or the radians. Although if you like, it's actually useful to memorize them both. But if you know just one, you can always convert into the other one using our formulas from the last part. Okay, so I'm going to draw this in 2 sets. The first one is easy to do because all you're doing in degrees is counting by 30. So 0 degrees. And what you're going to do is you're going to split each quadrant into 3 equal sections. You're going to split each quadrant into 3 equal sections. What these lines are is they represent the terminal rays of our angles. You say, well, why are terminal rays? Why not? Where's the initial ray? Remember, the initial ray is always on the positive half of the x-axis. That's what we mean by standard position. So here we're going to be drawing all of these angles in standard position. Okay, so we've cut up each quadrant into 3 even pieces. So 3, 6, 9, 12. And now you're going to do is you're going to count by 30. So 0, 30 degrees, 60 degrees, 90 degrees, 120 degrees, 150 degrees, 180 degrees, 210 degrees, 40 degrees, 270 degrees, 300 degrees, and 330 degrees. Once you get back to here, that's 360 degrees, which is the same as 0. That sounds strange. 0 is not equal to 360. Those are very different numbers. Right, that's true. 0 does not equal to 360, but 0 degrees is equal to 360 degrees, at least as far as a circle is concerned. When we say equal, when it comes to angles, we don't mean the numbers are equal. We mean that the measure is equal. All right? So here, if I have an angle that starts here and ends here, that's a 30-degree angle. If I have one that starts here and ends, always this starts here and it ends here, this is a 60-degree angle, 90-degree angle, 120-degree angle. We know where the initial ray is always going to be, so we just bother drawing the terminal ray. If you draw this angle, that's 0 degrees. Now if you go all the way around, that's 360 degrees, which it's technically different, right? It's a different number. You went all the way around. You did something that you didn't do for the first one, but in the end, they're both the same angle because they both have 2 overlapping lines. Right? These are what are called coterminal angles. Coterminal angles are angles that have technically a different measure because the number is different, but for all intents and purposes, they're the same angle. Right? So here, these are called coterminal angles. And those are defined as are angles in standard position. This is the definition. Coterminal angles are angles in standard position that have the same terminal side. So basically, they're kind of different because the number is different, but they're also kind of the same because when you draw them, they look the same. Right? So those are called coterminal angles. Examples of coterminal angles are 0 degrees and 360 degrees. But you know what? You could do that again. You could take this rotation and repeat it a second time, adding another 360 degrees, which would give you 720 degrees. That would be another coterminal angle. So even though the angle number looks different, technically the measures are different, in reality, when you draw these, they look the same. Also remember that angles can go in both directions. You have a positive angle by tracing it out counterclockwise, or you have a negative angle by tracing it out clockwise. So instead of saying I'm going to go 360 degrees this way, you could go 360 degrees the other way, which would make it a negative. So that would be negative 360 degrees. And if I go backwards once, I go backwards a second time. That would give me negative 360 and another negative 360. That would be negative 720. And every single one of these, even though the number looks different, they are drawn out exactly the same angle. As you can tell, there's no end to this. This could keep going. I could do a third rotation in either direction, and a fourth, and a fifth, and a sixth, and a seventh. There are infinitely many. So here, note, because we can go around the circle as many times as we want, including, thousands, millions, and billions of times, note there are infinitely many coterminal angles. But they're predictable because in order to get back to where I started, I either have to add 360 once or twice or thrice and so forth, or I have to subtract 360 once or twice or thrice or so forth. So even though there's infinitely many coterminal angles, they're predictable. Any angle can have any multiple of 360 degrees. So any multiple of, so either 360 times 1 or times 2 or times 3, any multiple of this number added to it to get another coterminal angle. So for example, if I've got 40 degrees, I could add 360 to this. Okay, so 40 degrees, that I could do 40 degrees plus 360, that's 400. I could add another 360. I could say 40 plus 2 times 360. Well, that's 720 plus another 40, that's 760. Or you know what? Instead of adding copies of 360, I could subtract. I could say 40 degrees minus 360 degrees. That would give me a negative angle. That would give me negative 320. Or I could do 40 degrees minus double 360 degrees. That would give me negative 720. That would be 40 minus 720. That would give me a negative 680, and so forth and so on. I could add or subtract 3 copies of 360, or 4, or 5, or 6, like that. And all of those would be coterminal to the angle 40. Because this is so predictable, we have a nice closed form way of writing it. So here, note, given an angle theta, theta plus or minus, you can go either way, plus or minus, plus or minus, 360 degrees times n is also coterminal. Where here n is any natural number. It can be 0, it can be 1, it can be 2, it can be 3, 4, 5, 6, 7, 8, 9, 10. Here n is any natural number. Okay. Let's go back to this. I said I was going to give this in degrees and in radians. Okay, well, we have all the degrees here. Let's do radians. Degrees were nice because all you have to do is count by 30. 0 degrees, 30, 60, 90, 120, 150 degrees, all the way around. Radians are going to be harder, yeah? Well, not really. You just have to count by sixths. You mean like sixth as in the fraction? Yeah. Oh, well, that is kind of hard, isn't it? Well, it can be, unless you just think about the numerator. Because here, 0 degrees is the same as 0 radians. I'll do this one I guess I'll do it in red. So this one in radians, this is 0 radians. And I'm not going to, we don't need a unit here. I could write rads, but I'm just going to write 0. Now, this is pi over 6. The next one, when you're counting by 6, you don't have to worry about the denominator. You just worry about the numerator. 1/6, 2/6, 3/6, 4/6. You say, what about pi? Pi is just part of the numerator, but that's just being multiplied by the coefficient of 1/6, 2/6, 3/6, 4/6, 5/6. So basically, I have this. I have 1 over 6, 2 over 6, 3 over 6, 4 over 6, 5 over 6, 6 over 6, 7 over 6, 8 over 6, 9 over 6, 10 over 6, 11 over 6, and 12 over 6. Now take those fractions, reduce them times pi. So 1 over 6 is already in lowest, it's already in lowest terms. So it's going to be 1 over 6 pi, right there. 2 over 6, oh, that reduces to 1 over 3. Okay, so in radians, that'll be 1 pi over 3. 2 over 6 is 1 over 3, so that's 1 pi over 3. 3 over 6, well, that's 2. Well, that's 1 over 2. Oh, don't forget your pi, so that'll be pi over 2. 4 over 6, that's the same as 2 over 3, so that'll be 2 pi over 3. 5 over 6, that's already in lowest terms, so this one will be 5 pi over 6. And 6 over 6 is 1. Okay, so don't forget your pi, that's 1 pi. And there we go. We're counting by sixth. It's just you got to reduce. But that is 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6. Keep on going. 7 over 6, that's already in lowest terms. Don't forget your pi. 7 pi over 6. 8 over 6, that's the same as 4 over 3. Don't forget your pi. 4 pi over 3. 9 over 6, that's 3 over 2. So that's 3 pi over 2. 10 over 6, that's 5 over 3. Again, don't forget your pi. 5 pi over 3. 11 over 6, that's already in lowest terms. So 11 pi over 6. And 12 over 6 is 2. Oh, well, that's times pi, 2 pi. And there we go. If you memorize the degrees, you can turn them into radians using our formula from before. If you memorize the radians, you can turn them into degrees using our formula from before. So you really only need half of these. However, it is sometimes convenient to know just both off the top of your head. But at the very least, you should know one of these. And these are common angles that you'll see a lot. But that's not the end of it. We do have one more set of common angles. Oh, let's see. I guess I'll use this marker here. Right here, what we did was we cut up every quadrant into into 3 pieces. 1, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, 3. Now what we're going to do is we're going to take the same quadrant, forget that these lines are there, and we're going to just cut each quadrant in half. So there, 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 and there. In degrees, this is easy because it's just halfway between 0 and 90. That's 45 degrees. Here, this is halfway between 90 and 180. Okay, well, that's 135 degrees. Halfway in between. Just add those two numbers and divide by 2. It's the average of those numbers. Halfway between 180 and 270, that'll be 235. 235. That'll be 225. I forgot how to divide. 225. And then halfway between 270 and 360, that one is 315. 315 degrees. For radians, they're just odd number times pi over 4. So this one is 1 pi over 4. This one will be 3 pi over 4. This one will be 5 pi over 4. And this one will be 7 pi over 4 for radians. This, of course, is not every possible angle. Obviously, we could have 12 degrees. Obviously, we could have pi over 17 radians. We could have 1 radian. Right? We can have any number, not just the ones on here. But these angles are going to show up more often than any other angle is going to show up in application, as you'll see as we go through this course. So here, these angles are ones that you want to remember. At the very least, remember either the radians or just the degrees. If you have desire to, you can of course remember them both. And note that everything we said down here about degrees is also true for radians. The only major difference is going to be 1 full revolution of a circle is 360 degrees. For radians, it'll be 2 pi radians. So down here, given an angle theta, theta plus or minus 2 pi times n is coterminal. So if I have, let's say, pi over 3 radians, then a coterminal angle would be take your pi over 3 and add 2 pi, or add double that, 4 pi, or add triple that, 6 pi, or negative. You could subtract 2 pi or 4 pi or 6 pi. So any of those would work. I could have 3 pi plus 2 pi. I could have pi over 3 plus 2 pi. That's going to give me 7 pi over 3. I could add another 2 pi. Instead of adding 360, and I could add double 360. I could add 2 pi, or I could add double 2 pi. That's 4 pi right there. And 4 pi plus pi over 3. Oh, that'll give me 13 pi over 3. And of course, I could always subtract. I could say pi over 3 minus 2 pi, or double 2 pi, or triple 2 pi, or whatever I like. If I do triple 2 pi, that's going to be negative 6 pi. And then I add pi over 3. That would give me negative 17 pi thirds. Negative 17 pi thirds. All right, so big takeaway. For any angle, add or subtract any multiple of 360 degrees, you're back where you started. Or if you're in radians, add or subtract any multiple of 2 pi, and you're back where you started. Your number might be different here, 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 and here. The numbers are different, but the angles are the same. Say that here, all these numbers are different, but the angles are the same. Okay. Now, a moment ago, I said that there's 2 ways of measuring angles. You have degrees and you have radians. And there's reasons why we have both. I said degrees are usually easier for people to remember. 30 degrees, 40 degrees, 60 degrees, 90 degrees. Radians, they're a little more difficult to visualize, if nothing else. Pi over 4, pi over 3, pi over 2. I can easily remember that's 90 degrees. And by comparison, 45 degrees must be half of that. On the other hand, 2 pi thirds radians, I have a little bit of a hard time remembering exactly where that might be. So from just a very quick heuristic standpoint, degrees tend to be nicer. But radians have their advantage too. And that is, if you're thinking in radians, a lot of computation is much nicer. Let's take a look at some applications of radians now, because the formulas that we see in this course are much easier if you think about them in radians. All right, so let's look back at a previous result here. Earlier, when we defined a radian, we said that the measure of any angle is equal to the arc length of the arc that the angle intersects divided by the radius of the circle. And on a unit circle, since the radius is 1, dividing by 1 doesn't change anything. So at least as long as you're on the unit circle, this theta is equal to this s. This might be in inches and this might be in radians, but the number's going to match. Okay? But if you're not on the unit circle, well, then you just do s over r. Okay? Well, then that's a formula. Here, since on a circle of radius r centered on the origin, we intersect an arc of length s using an angle, I don't know how to spell, let's try that again, using an angle of measure theta then theta is equal to measure of theta radians. That's got to be a measure of theta radians. Won't work in degrees. Then theta is equal to s over r. So if I take this r and multiply it to the other side, we get the S by itself is equal to R times theta. But then that's a formula for arc length. So for example, let's say we have a circle where the radius is 5. We have an angle that crosses this circle, and the measure of this angle, now it has to be in radians. Here, this definition was in radians, not in degrees. So here, let's say this is pi over 3 radians. Then the arc length here, so this is the number 5, that's the radius of our circle. The arc length S is nothing more than the radius of the circle times the angle in radians. So that's going to be 5 times pi thirds, and this is 5 pi thirds. That's the length of this arc. Note that if your angle starts off in degrees, you can still do this, but you have to convert to radians first. So for example, if I have a circle here of radius 3, and I have an angle that crosses my unit circle, and it has a measure of, let's say that's 200 degrees, like this, or 200 degrees. That would be between 90 and 180. So that would have to be maybe, let's do 150 degrees. Okay, so this would still work. We just have to convert to radians first. So 150 degrees, remember to convert from degrees to radians, you need to multiply by pi over 180 degrees. So 150 over 180, that reduces down. That's going to give us, I can divide top and bottom by 30. So that'll give me 5 pi over 6. So even though right here I have 150 degrees, which is a little hard to read here, even though we have 150 degrees, we're not going to use 150, we're going to use 5 pi over 6. So here this arc length that we're intersecting, S is equal to R times theta, which is going to be our radius 3 times, don't use 150, use 5 pi over 6. And that gives us 15 over 6, which reduces to 5 over 2. So we end up with 5 pi over 2. And that would be the measure of this length here on the outside. But that's not the only thing we can measure. Right now we've been looking at exclusively the outer edge of our circle. We've been looking at this arc length and how the angle inside can allow us to measure along the outside. But when we look at this circle, something else we can measure about the circle inside of this angle is not just the outer edge, but all the space inside. Okay? That space inside, this slice of our circle, is what's called the sector. Okay? So whenever you have a circle and you cut it into wedges that all meet at the center, imagine slicing a pizza. Imagine slicing a pie. Doesn't matter how many slices you cut it into. Maybe they're not even all equal in size. Some are a little bigger, some are a little smaller. As long as they all meet at the center of the circle, each one of these is called a sector. Okay? So what we can do is we can measure the sector of a circle in a way that's similar to what we've seen here. Okay? All right, well, how would we do that? Okay, well, a sector is just part of the full area of a circle. Now recall from geometry, the area of a circle that's given by pi r squared. Okay, well, then our sector must be some fraction of that. If our sector looked like, for example, this right here, then it would be half of that area. If our sector looked like this, well, then it would be a quarter of our area. This might be an eighth of our area, or a 12th, depending on how big it is. Oh, well, depending on how big it is, depends entirely on the angle inside. Because since all of these meet in the middle, that means all of them have the same radius distance from here to the outer edge. From the center to the outer curve, to the outer arc, that distance must be the same. So the size of this sector relative to the whole circle, whether it's half or a third or a quarter, depends entirely on what percentage of the circle it is, and that's given by our angle. Okay, so what we're really looking for here, the area of our sector, that's going to equal to the area of our circle times what fraction of our circle we have. So if we have half of our circle, it'll be half times the area of the circle. All right, if the area of the circle is 50 square units, and this sector is a quarter of that, well, then we'll have 1/4 times 50. Right? We would have 12.5 square units. So this is what fraction of the circle we have. Oh, but we can measure that very easily, because what fraction of the circle we have is simply going to be what angle we have. That's theta. That's how we measure our angle. That's theta, divided by the total possible measure all the way around. Well, in radians, the total distance around a circle is 2 pi radians. So if, for example, the angle that I'm measuring out is pi, if I take pi divided by 2 pi, the pi's cancel out, and I just get 1/2, which that's correct. That would be half of a circle. If I had pi over 2, that would be right here, this angle here, the same as 90 degrees. If I had pi over 2, and I was dividing by 2 pi, the pi's would cancel, leaving me 1/2 divided by 2, which is 1/4. And that is accurate. That would be a quarter of our circle. Okay, so this right here gives you what fraction of the circle you're looking at, times, well, the area of our circle is pi r squared. Here, the pi's cancel out, and we're left with a formula for the area of a sector. So the area of a sector, that's area equals, we've got a 2 left, but it's in the denominator. So 2 in the denominator, we're dividing by 2. So we can do everything divided by 2, but usually the formula is written as 1/2. That's fine. Dividing by 2 is the same as multiplying by 1/2. So it's 1/2 theta r squared. But this does depend on this measurement being in radians. If you do this in degrees, this doesn't work. If you have a measure in degrees, that's fine. You just have to convert it to radians first. So this is our formula for the area of a sector. And keep in mind that it does have to be in radians, where theta is in radians. So let's go ahead and take an example of that. If I have a circle, a disk, where the radius of that disk is 8, and then I have an angle, a central angle. Remember, it does have to meet in the middle, so this does have to be a central angle, that has a measure here of pi over 4. Then the area inside of this sector is going to be 1/2 theta r squared, which is 1/2. Theta is this pi over 4. R is 8, quantity squared. So here 8 squared is 64. Okay, so that'll give me 64 pi on top over 2 times 4 is 8 on the bottom. Those are the denominator. 64 divided by 8 is 8, and don't forget your pi. So here this would be 8 square units, since we're talking about an area. Here, let me actually give a unit. Let's say this is in inches, like an 8-inch pizza. So here this would be 8 pi square inches would be our area. This does work just fine in degrees. You just have to convert to radians first. If it's not in radians when you plug it into your formula, that just won't work, because this formula is dependent on having theta in radians. So here I can have a 12-inch slice here, and I've got an angle of, let's do 3 pi over 4. Okay, so that area, let's do it in degrees, that way we see the conversion. So let's say that one is 135 degrees. So that our area is equal to 1/2. Do not use 135, that'll be way too big. We need to convert to radians first. So we're going to take 135 degrees. To go from degrees into radians, we multiply by pi over 180 degrees. And so here, 135 over 180, you can divide top and bottom by 45. That gives me 3 pi over 4. 3 pi over 4. So that would be our degrees. Do not, that would be our angle. Do not use degrees. Here we do 3 pi over 4. And then r is 12 squared. Here we can go ahead and square that. 12 squared, that's 144. Okay. Let's see. I can actually reduce that a little bit. So this is half times 144. Half of 144, that's just 72. That's 72. And 4 goes into 72, what is that, 18 times? I think that's right. 72 divided by 4, that's 1. That's 8. No remainder. So yeah, that's 18 times. So 72 goes into 4 18 times. And so I'm just left with 18 times 3 pi. 18 times 3, that's 30, 40, 54. So I end up with 54 pi. And so 54 pi, we'll do that in inches as well. And so our area would be 54 pi square inches. Just like that. And you can make things slightly more complicated. So for example, let's say I had a circle. And this circle had a radius of, let's say, 10 inches. And I wanted to find the area of this right here. You say, well, just use your sector formula. Yeah, but this thing that I've shaded in is not a sector. Here you can imagine this is a pizza. Here's the part with the cheese and the toppings, and here's the crust. What I want to do is I want to figure out how much crust I have here. What's the area of the crust? So that's definitely not a sector, because a sector has to come all the way to the center here. And you say, okay, then how do we do that? Well, here we're going to need one more measurement, and then we can do it. Let's see. So this is 10 inches here. What we're going to need is this distance here. We're going to know that that one is 8 inches. So the crust is only 2 inches thick, or 2 inches wide. And then here, let's go ahead and put this as pi over 6 as our central angle here. Okay, so now we can use our sector formula. You say, no, you just said that's not a sector. That's true, that's not a sector. But the whole thing, including the crust and the center part, this whole thing is a sector. Yeah, but I don't want the whole thing. This little piece that I don't want is also a sector. So what I can do here is I can take the big sector minus the little sector. And what's left over is my crust. Basically, I take the whole slice, I eat the part with the toppings and the cheese, and what's left over is my crust. So here we go. The area that I want, I'm going to use the formula twice. Once for the big area. Okay, well that's 1/2. Theta is pi over 6. For the big sector, the one that includes everything, the radius is 10. Don't forget to square that. For the smaller sector, the one that doesn't include the crust, I'm going to have 1/2 times pi over 6. My radius here is just 8 squared. Notice here that 1/2 times pi over 6 is common to both. So when I subtract, I can pull out a common factor. Oh, let's see, that's 1 pi over 12. That's 1 pi over 12. So 1 pi over 12 is a common factor. If I factor out 1 pi over 12 here, I'm left with 10 squared. minus, if I factor out 1 pi over 12 here, I'm left with 8 squared. And in general, that's how that works. You're going to have a similar formula. You're going to have 1/2 r theta squared, 1/2 theta r squared, but instead of having just a single r squared, you're going to have the bigger r squared minus a smaller one. So here we go. This gives us pi over 12 times 100 minus 64. That gives us pi over 12 times 100 minus 64, that's 36. And we multiply. 36 divided by 12 is 3. So here 36 over 12 is 3, and don't forget your pi. So in the end, I had a bigger sector, but when I took out the smaller sector, that little crust in red there was left over, and that gave me an area of 3 pi square inches. And that makes us happy. But there are still further things that we can measure using our radian measure. For our next topic here, let's talk about speed. In particular, let's talk about two topics called linear and angular speed. Okay. Consider this setup here. Got a little circle. Oh, it's got a radius of, I have no idea. It's 2 inches. It's a 2-inch radius. Now, if I measure out an angle by spinning around this way, and I say, how fast is that going? How fast am I going around my circle? Well, I could answer that a few different ways. I could say, well, let's see. How long did it take you to go all the way around the circle? Oh, let's see. Go ahead and start now. That took 2 seconds. Okay, so you're doing 1 full revolution every 2 seconds. So you're doing half a revolution a second. That's one way I could measure it. That's perfectly fine. That's a reasonable answer. But there's another way I could answer it. I could think of it in terms of this outer point. I could imagine I have a little bug right here, a little ant. And that ant is going to walk around the outside of my circle at the same speed as the metal is turning. So as I go around, I could say I made a full revolution in 2 seconds. That's 1 revolution every 2 seconds. That's half a revolution a second. Or I could say, well, my radius was 2, and so my circumference was 2 times pi times my radius, so 4 pi. And so 4 pi is how far the little ant walked around in 2 seconds, which means he was walking at a speed of 2 pi inches every second. And that's also a reasonable way to answer that. How many revolutions do I make versus what's the distance that those revolutions cover? That's the difference between angular speed and linear speed. Angular speed is measuring how many times around do you go? How fast are you going around? Oh, you make 1 revolution a second. You're making 10 revolutions a second. You're making 1,000,000 revolutions a second. On the other hand, linear speed doesn't worry about the angle. It worries about the actual distance. Oh, you went around 12 inches in 1 second. You went around 50 inches in 1 second. You went around 2 million inches in 1 second. Linear speed is the distance, is a speed around the outer edge. Okay? So as a point moves along a circle of a radius, a circle that has a radius of r, you have a radius of r. The angular speed, the symbol for angular speed is given by omega. Omega? Yeah, that's just the Greek character. It looks a lot like the letter W, except it's more curly. If you want to use the letter W, that's fine if you're not used to writing this out, but formally it's the letter omega. So here the angular speed, the symbol is omega, and it does look a lot like the letter W, except it's a little more curly. In fact, a lot more curly, like that, is equal to theta over t, where theta is your angular rotation. It's the size of the angle that you went around, and t is the unit of time. Oh, it's that many radians in 1 second, or that many radians in 1 minute, or 1 hour, whatever your unit of time is. So here theta is an angle measure, and we're going to do this in radians. And t is your unit of time. On the other hand, your linear speed is just the distance traveled. It has nothing to do with an angle. Linear speed, even though you're not actually following a line, but it's linear speed as in a straight line distance speed. That's going to be given by v equals s over t, where s is the arc length. It's the actual distance around the outside. And t is, again, the unit of time. Hours, minutes, seconds, or whatever it might be. Whenever the angular speed is measured in radians, and again, it does have to be in radians, then you can actually relate these two values. If theta is in radians, which we're going to have it be in radians all the time, then your linear speed is equal to your r, which is the radius of your circle, times your angular speed. Which makes some sense. If I have this same circle here, and I'm tracing out an arc like this, I'm tracing out an arc. If I put my finger over here, where the radius is small, this is maybe 1 inch, I barely even feel it touching my finger. But if I keep the exact same angular speed, but put my finger up here, that actually kind of stings a little. It kind of hurts. Because even though the angular speed is staying the same, here, the distance is much smaller. I barely feel it. Up here, even though it's the same angular speed, the same omega, having a larger r gives me a bigger linear speed. Okay? So let's go ahead and look at some examples of this. All right, let's say you had a bicycle wheel, and that bicycle wheel is turning. Like this. So a fairly popular size for a bicycle wheel is a 29-inch wheel, which means 29 inches is the distance all the way across. Okay, but all of our formulas use a radius. Okay, well that's half of the full distance across. If the full distance is 29, that means this one's going to be 14.5. Okay, so this would be a realistic size for a bike wheel. This is a pretty popular size. You have a 14.5-inch wheel. Now you're going to have it spin around, and it's going to spin around. Let's say 30 times a minute. Okay, so here, this wheel spins 35 times per minute. Let's go ahead and find both the angular and the linear speed. Okay, all right. So here, if I'm going to spin 35 times a minute, my angle, every time I spin around, and again, we're doing this all in radians, that's going to be 2 pi radians all the way around. Okay, so 1 revolution of the wheel, that's going to be 2 pi radians, which means that 35 revolutions, which is how many I make a minute, is going to equal to 35 times this 2 pi, which is 70 pi radians. So that's how many radians I'm going to spin around. Oh, but that happens every minute. So that's going to be 70 pi radians per minute. So what are we looking for here? Angular. So my angular speed, which again, the symbol for that is omega, is given by 70 pi radians per minute. But we can find linear speed because since our angular speed is in radians, we simply now need to multiply this by the radius of our circle to find our linear speed. Since omega is in radians per time, so here this can be hours, minutes, seconds, doesn't matter, as long as the top part is radians, then our linear speed is equal to omega times r, which we know omega is 70 pi. Our r is going to be 14.5, like this. And that gives us, let's see, 7, 8, 9, 10, 15. So this gives us 10, 15 pi. Now here, this is in radians per minute. Now remember, radians, we write radians just for the sake of writing something. But remember, radians are not a unit. They're just like a description of what we have. But this is not an actual unit. So here, this is 70 pi per minute. Here, 14.5 is an inch. So this is inches per minute. I know it's a little strange to write it that way, but radians aren't actually a unit. They're just kind of a description of what we have. But when we say 70 pi rads per minute, we really mean 70 pi per minute. It just sounds so weird to not have something on the top. Usually we have, inches per minute or feet per minute or, pounds per minute. So we say rads to make it sound more familiar, but really this is 70 pi per minute. There's no unit here. So this is inches per minute. And this would be our linear speed. We can take this a little further, since I've already mentioned a bicycle wheel. There's lots of spinning things on a bicycle. For our last problem for this section, let me go ahead and combine these together here in a slightly more advanced problem. Let's say you have a set of gears on your bicycle. Okay, so the way this works is you have a big gear that your pedals are attached to. And you're going to spin this around with your feet, with your legs. And then there's another one back here that's connected to the actual wheel itself. So that is like right in the middle of your wheel. Okay? And then there's a chain that connects the two of them. All right. So now, let's say this thing right here has a diameter of 8 inches. So the diameter would be 8. So here you would have 4. So this is a 4-inch radius. And back here you have something with a diameter of, let's say that's 2 inches. So the radius is just 1. Okay. So here, this is connected to your pedal. And your pedal comes down here, and there's one on the other side. And you spin this one. Okay, and as this one spins, it's going to pull the chain, and the chain will make this one spin. All right, so we're going to go ahead and spin here, and we're going to spin decently fast. Let's say we're spinning this, let's keep it a nice round number. Let's do 60 times in a minute. So you pedal 60 revolutions. This goes around 60 times. Per minute. Okay. The question is, if this is going around 60 revolutions per minute, what is the angular speed, not of this one, but of this one back here? What is the angular speed of the small rear cog? Okay, so let's take a look. First of all, we have an angular speed right here. Right? This angular speed is going to be 60 revolutions per minute. Yeah, but for our formulas to work, we need to be in radians. Okay, so 60 revolutions per minute. Well, there's 2 pi radians per each revolution. So if we multiply those together, revolutions cancel out, and we get 120 pi radians per minute. Okay, so that's how quickly this one's moving around. It's going around at 120 pi radians per minute. Oh, but then that spinning is making this chain move. But this chain isn't moving with a linear speed. It's not moving with an angular speed, it's moving with a linear speed. We can measure how much chain is going through. It's 2 inches every minute, it's 10 inches every minute, it's 50 inches every minute. Oh, that's a linear speed. So now looking at our chain, so this is our angular speed of the large front cog. And now we can look at the linear speed of the large angular cog. Because since this chain is being pushed through using this big cog, the linear speed of the outside of the cog will be the same as the linear speed of the chain. It'll tell me how quickly the chain's moving. Okay, so now let's take that 120 pi, and that's radians per minute. And we know that linear speed is given by that angular speed times the radius of that wheel. In this case, 4 inches. This is going to be 4 inches. So 120 times pi times 4, that gives us 480 pi. And again, radians aren't actually a measure. They're just kind of a placeholder. So here this is blank per minute. So the inches take the place of that blank. So the linear speed of this wheel, which means it must be the linear speed of the chain, is 480 pi radians. Oh, sorry, not radians. Inches per minute. But if that's the linear speed of this wheel, then that's the linear speed of the chain. But since the chain is also connected to this wheel, that must be the linear speed of this wheel also. So this is the linear speed of the big cog, but also the chain. But since all three of them are tied together, that's also the linear speed of the small cog. Okay. So now we know the linear speed of this. But now we can find the angular speed very simply. Because after all, we just saw back here that if we have a linear speed, that's equal to the radius times the angular speed. Okay, well, I have the linear speed here, and I have the radius. I want the angular speed. I want to find omega. Okay, so let's divide the r over. Here, this formula can also be written as omega, our angular speed, is equal to v divided by r. So here, that means that if you take your linear velocity that we just found, 480 pi, and then divide that by the radius of our small wheel, which is only 1 inch, so that's just 1, that's going to give us, let's see, that's inches per minute. But then we're dividing by 1 inch, so that's going to get rid of this here. That's going to get rid of this here since we're dividing out the inches, and that leaves us a unitless measure over minutes. Or a unitless measure for an angle, that's got to be radians. So here that gives us 480 pi, 480 pi radians per minute. So here, if you pedal this one 60 times every minute, the angular speed back here will be 48 pi radians per minute. Oh, but one of these little wheels is tied to this big wheel. This little wheel right here is a cog. It's a little tiny metal-toothed wheel that's in the middle of your big tire. This is the tire, the one that actually touches the road. Okay, well, these are stuck together. So if there's a point right here and a point right here, when this rotates one time around, this rotates one time around. So your wheel, the one that's actually got the tire on it, the one that's making contact with the ground, has the same angular speed as this one does. Because if this little one rotates once, the big one rotates once. So this one right here must have whatever its angular speed is. That's got to be the same as this angular speed. If this goes around once, this goes around once. This goes around 50 times, then so does this one. So now that we know the angular speed of our little rear cog, we can now go ahead and find the linear speed of our big wheel. Okay, so the linear speed of our little cog is 480 pi. So 480 pi rads per minute. This is the angular speed of the rear cog. But that means it's also the angular speed of the rear wheel. So now we can find the linear speed of the rear wheel. In other words, we can figure out how fast your bike is going. So here, the linear speed, again, that's going to be your radius of your wheel times your angular speed. Okay, well, we know the angular speed. That's 480 pi rads per minute. And we have the radius of the big wheel. That's 14.5 inches. 14.5 inches. And so here we end up with inches per minute. And that's going to be, let's see. That's 6960. So this gives us 6960 pi inches per minute, which that would be the linear speed of your rear wheel. You can always convert this into miles per hour if you like, but we're not going to worry about that. So this would be the linear speed of your actual wheel. But that is pretty fast. That's just a hair over 20 miles an hour. So this the numbers I put in here might be a little big. It's kind of hard to get up to that speed, but it is not unheard of. So in any event, that is it for this problem. In fact, we did one extra piece. The question was only asking to find the angular speed of the rear wheel, of the rear cog, which we did that here. That would have been the end of that problem. And then I figured, well, since we already have that, we could take one extra step and actually figure out the linear speed of our rear wheel. But that actually was one extra step beyond what the problem originally asked. So that is it for this section on definitions and basic formulas and basically an introduction to everything you need about angles to get us started for this course. If anybody has any questions, comments, or problems, please reach out, and I hope you all have a nice day.